Voy a empezar con una anécdota muy rápida.
I will give you a brief introduction, historical introduction. The first railway that there's evidence from is from the year 600 before Christ in the ancient Greece, and it was a 6-kilometer section that was used to transfer ships to avoid a much longer sea route. Cybersecurity wasn't great at the time. It wasn't a concern at the time, but it appeared apparently they were great in physical safety. So I'm going to skip this slide quite quickly. I tell very terrible jokes about trains and Greeks. I've spent a few years working in Switzerland. That since last year I've started working in Selectron. And this company, Selectron, contacted me and asked me whether I wanted to keep on working in cybersecurity but start working in the railways. And it felt like a great idea. Is there anybody in the room who does not like cybersecurity or trains? Well, then you're not in the right place then. So what is this company, Selectron? It's a small Swiss company, 150 employees, and they develop automation elements for trains, for railways. They are PLCs, so computers to control applications or functions within the train. It's part of a bigger group, Norbrems, which is a huge group with many other companies. Meda, which is a Spanish company here in Getafe, they take care of air conditioning equipment. ICE, who makes doors, another one for brakes. So all the components within. In the value chain, we have passengers and goods, then train operators and infrastructures. In the case it would be Renfe and Adif, train builders in Spain. We have Talgo or CAF, and we would be at the bottom as components builders. So we are we sell our products to the companies that manufacture trains, and they sell it to the operators. So what am I going to talk about? I'm not going to talk about the corporate way and the web pages that they have to sell. The companies have to sell tickets and provide information to users, and I'm not going to talk about Irene from Renfe, although it might be of some interest. I'm not going to talk about the operations part, where there are sometimes very old material, where the scheduling is done of the traffic, the train traffics, where each train should be at each point in time. And I'm going to focus on engineering. And engineering, there are two parts, the signaling part and the onboard system. We're going to look at signaling, and then I will focus on onboard systems, which is what Electron develops. What should we take into account if we think about cybersecurity in the railway world? Well, many things, but I would like to focus mainly on two. One is automation of railways. You all know many examples of subways or tramways that work autonomously, and the same thing applies as in the cars. We can go from assistance to driver to a train that works in a completely autonomous way. And the greater the automation level, more relevant is cybersecurity going to be, because the potential impact will be obviously greater. And then there is another very marketing-like area, which I'm not going to mention here, which is mobility as a service, and it's very trendy. And what it generates is a need for interconnectivity in vehicles and trains that in the past were not supposed or were not going to be connected to external networks, but there's an increasing need for that to change and to have interconnectivity, be it to provide services to customers or passengers, to get higher invoicing, or to do predictive maintenance and other functions that may need to be implemented. So we're going to move on to signaling. What's signaling in the world of trains? And what's it for? Initially that didn't exist until the Armagh rail disaster happened. This was in Ireland in the 19th century. It was at the end of the 19th century. It was a train that was struggling to go uphill, and they had to stop it, and the passengers on the back wagons had to go to the head ones, but those wagons were not properly stopped, and they ended up crashing with the following train coming along the track. So there were 80 victims and fatal victims and many injured, and that's why the legislation was changed and signaling came about. So what's it about? You actually define a number of blocks whose size is determined by the braking distance that the train needs. And if we're talking about a high-speed train, they are going to be longer distances than regional trains. And what we do is that if a train is on a certain block, then the signal will indicate red. And even in the prior block, there's going to be a limited speed allowed to guarantee that there is the braking space margin. And not only do we control when the train has gone by, but in each transition between blocks we look at the intensity of the train, so that if there is one wagon that's or one carriage that it's at still in the prior block, then that block is still considered as busy. That generated problems. Just one more problems for the standardization of the railway in Europe. One more, because there are things like the railways sizes, etc. And that's when the ERTMS was created, the European Rail Traffic Management System, to make sure that we are all using the same way of controlling the signaling system. And with this, it is a lot easier that if a train has to go from Spain to France, it can do it without obstacles. This standard defines 3 levels. The level 1 is the one I've just explained. It uses the traffic lights and the earth line to make the control of when a train transfers to the next block, and there's not much more complexity to it. But if we look into levels 2 and 3, which are already being used, the level 3 not yet, but the level 2, for instance, the high-speed train, it's used in the level 2 of ERTMS. We see as main novelty that traffic lights are no longer needed, and because there's this signal that's sent to indicate whether you can keep on advancing or you have to stop. And in terms of security, this is interesting because we see that there is a certain remote connectivity or mobile connectivity, and the standard used for this communication is the GSM GSMR. It's like the mobile ones, but with some changes. Then we have the Euro radio level, which is the one that signs the message, and at the end it has an MAC to guarantee who has generated that message, and then the application layer on top. GSMR uses the same encryption as ERTMS, and that's not particularly important because there isn't confidential information there. And to calculate that authentication code, the MAC, we use the standard cryptography algorithm based on the ISO 9797, but they decided to innovate that standard and improve it, and perhaps they would have a benefit from having this certification on cryptology, because what they thought was a good idea, that is to change the original algorithm, which is using a triple desk at each level, to make it more optimal in terms of output by to use a triple desk only in the last iteration. What could go wrong? I don't know if it was last year or 2 years ago, but this paper was published and it's on internet. You can take a look at it. What the team did was to prove that you can snip the packages and you can decipher them easily. And due to the change they did in the algorithm, it's quite easy to recover the key that they used in a particular session to calculate the MAC code and to use it at the end to generate a package and sign it, and for the train to consider it valid. And with that, you can tell the train to keep on going at 150 kilometers per hour, even if there's a train stopped further ahead. In theory, this is very easy to do, but luckily enough, it's not in practical terms. It's not so easy, and it's not so because the volume of data is there's not time for the whole chunk of data to be transferred. But nevertheless, this was an awareness-raising point in terms of the security of the system. As lessons learned, I'd say that if you want to do something about cryptography, it's a good idea to have experts in the team. This is not the only problem, but at the end, because of safety reasons, the systems are designed so that if communication, GSM communication stops, the train stops, because there's no way to know if the next block is busy.
Incluso yendo más allá.
And beyond that, the messages that a train gets to stop, even though the mark may not be valid, the train in general, at least according to the standard, will consider those messages valid and it will stop, just in case there is some sort of problem in calculating that mark code, and in case the train, so that there won't be any safety issue for passengers. And that means that doing a denial of service to a train with level 2 or 3 of GSMR is as easy as using a GSM jammer. And one of the main research lines that operators have had, which is due to many of the pains they've got, or which causes many of the pains they've got, is to try to identify and prevent these attacks. This is illegal, by the way, so if you're planning on playing with that, please take that into account. And here we have the example of a signaling network of a very small operator, a metro operator. I just found it on the web, actually. I haven't actually talked to them, but I thought it was a good example, because eventually it's just a relatively small facility where installation is a tram or a metro. It's just limited to a city, and it has certain complexity. When we aim to extrapolate this to a national operator such as Renfe in Spain, the network complexity of those systems, of those signaling systems, is massive. And here I'm just generalizing, but each operator eventually is different. They may implement things as they wish. But usually, in these cases, we just find flat networks without segmentation or with very slight segmentation, without coding, with MTPLS connectivity due to the geographical location. And regarding the interlocking teams, maybe they date from 1950s or 60s, they cohabitate or coexist with current systems. That may be from Windows Server 2016 or 2003, Windows XP, Windows NT, or Windows 98. This has been acknowledged by operators to whom I work. None of them has said that they've got Windows 95, but maybe there are some of them around the world who have that in their signaling systems. And this is pretty much it regarding signaling. I'm not mentioning too many details, and hopefully for next year's round, or for next year's RootedCON, someone could take my place and come here with a cool piece of research. But I'm going to talk about onboard systems and networks now, because I think that part is even more unknown for most of us. At least I didn't have a clue until I began working as Electron regarding how these systems work. So first of all, these are real-time systems and protocols. What does that mean? Basically, in these systems you have limited time. In the railway environment, that is measured in milliseconds, even though in other sectors we could talk to different measures, but we talk here about milliseconds in our case. And in that space you need to get a signal, process it and give an answer. If it is not able, depending on the design, it might go to a controlled error system and it will stop doing the usual operation. What does that mean? What does it mean regarding security? Well, it means that any security measure with a security clear control that we want to implement in these systems needs to be able to comply with this real time. If you want to have ciphering, authentication, signing, or real-time analysis of memory and its forensic security control, eventually we need to make sure that that will not interfere regarding the performance with real time. And as you may imagine, that is a challenge when you begin looking at how to implement cybersecurity in these systems. And eventually, what do we do? Well, I've brought here an example. Maybe you can pat it around and have a look at it. And this is just a computer. It's a new PLC generation. It's just a prototype of what Electron is developing. And it's much more powerful regarding processing calculation than former versions. And this allows to actually virtualize PLCs and to have several systems and several PLCs in the same hardware. It even allows having different safety measures, running PLCs with a different level of safety than other PLCs. And I can give you more details about this later. But it is still a computer, and we have different types of PLCs in a railway or a train. The main one is the VCU, the Vehicle Control Unit, which is like the brain of the train. But you can also find PLCs dedicated to air conditioning, or to keep the train on the rails, or things that have to do with the brake. It all depends on the train driver, and it depends on whether they want one single system or different systems, because they may belong to different component factories. And network-wise, these systems always be redundant in trains, and regarding PLCs, 90 or 95% of the time they are usually found in high availability in a strong master weak master format, which means that both systems, both the strong and the weak master, are receiving the signals of the subsystems, are processing them, but only the strong master gives an answer eventually. So if the strong master drops, the weak master can take his place and keep the processing at the same place where it was, and I can let you decide who is the strong master and the weak master in this case. And what are these systems for? What do they control in the train? A bit of everything. It depends on the degree of automation implemented in the train, whether it's fully autonomous, they'll control everything. Otherwise, usually control the toilet systems, the braking systems, the traction systems. It's not like ABS, but it kind of avoids wheels getting blocked, because the problem here is that if they ever get blocked due to the strength of the friction, because it's steel against the steel, they will stop being round, and that is a problem for the train. They also control the conditioning, system doors, and so on. And earlier, I forgot to say that why real-time processing is needed and what's the reason for that. It is not always necessary, but in some cases, if we take the example of brakes, we need that real-time because applications need to be able to give a pretty much immediate answer. And now it's quite common for trains to have an application that is receiving the speed of each axis of the whole train wheels, as well as the individual speed of each axis, and with this information they process and determine which is the exact braking power they need to apply at each axis, and this changes in milliseconds. At each point in time they need to be able to indicate to each brake what's the power that needs to be applied for the brake to be optimal. And taking the systems into account, how they work network-wise, and which kind of networks can we find in a train? Well, there are different types of networks. One of the ones is the consist bus or the vehicle network. You may find one, the other above. It depends on the manufacturer, but this is a network where you implement these kind of systems. So we found the PLCs, the control systems, also the input and output systems that connect to the electronics for lights, doors, brakes. So this is one of the most critical networks in the train. And depending on the train, we can also find non-critical networks, also called comfort networks, that may be used for video surveillance, for information systems to passengers, and even to provide Wi-Fi services to passengers. Things that are not critical, that do not affect the effective control of the train. And then we have a specific train bus, which is a network that goes from end to end of the train, which is dynamic, while the consist bus is a static network that is not device to be changed frequently. You have the cabling and the configuration. You may have fixed networks on different devices. However, the train bus is a bus that can be self-calculated whenever the train configuration changes, whenever there are more carriages or less carriages, or whenever the direction of the train changes. And that is done through a process called train inauguration. And there, each train node shares with the rest of the train nodes in that train bus all the information they have on the configuration of the underlying network, the consist bus that they're connected to. And with this information, each node above
que veis arriba en la red Ethernet guarda una base de datos con
In that
toda la
net
información
keeps a database with all the train information. So regarding the train topology, and that is an essential process for trains.
desde el punto de vista de seguridad también
And from the security perspective, it is also one of the processes that may help a potential attacker to understand which is the topology, the exact topology of that train.
Si echamos un vistazo
And if we look at the protocols, at the physical interface link and the protocols,
depende al final un montón de cada fábrica
things really depend on the manufacturer.
qué tipo de protocolos
They decide which type of protocols they implement. But you may have protocols based on Ethernet, on CAN, and also specific protocols for the railway world that can only be found here, such as MBVV or WBTV. And depending on the protocol, they may be specific too.
también que no todos los protocolos se pueden
And then not all
utilizar,
protocols
tanto a nivel de red
may be
de
used
vehículo como a
on
nivel
network
de
level, vehicle network level, and a train network level. Some of them are specific for one or the other type of network,
muy utilizado y se puede
and
utilizar
there
tanto
is
a nivel
one
de
that may
red
be
de tren
used
como a nivel de
regarding
red de
train
vehículo.
network or vehicle network,
Es
the
un protocolo que se
TRDP.
utiliza para intercambiar
That
datos
protocol is used to
entre
exchange
las
data
aplicaciones, un
amongst
protocolo basado
applications,
en Ethernet,
and that is an
tanto
Ethernet-based
TCP,
protocol that uses TCP
como UDP está basado en un estándar,
and
que
DP.
tampoco hace falta
UDP
hacer
is
ingeniería
based on
inversa
a
para
standard.
hacerlo.
We don't need to do reverse engineering because the full specifications
Si
are
echamos un
public.
vistazo a nivel de seguridad, de ciberseguridad, cuáles son las principales características, pues
Regarding security and cybersecurity and its main features, the presentation will be very quick because there is no authentication,
Telnet a su lado, pues
and Telnet
por lo menos
next to it is a secure protocol because at least you have a password and a username. Here in this case you don't have absolutely anything.
y no es que le tenga manía a ese protocolo.
It's not that I hate that protocol, I just chose a random one that is the one that I've worked the most
Cualquiera de los protocolos que
with lately, but if we look at any of the former protocols, we'll be in the same situation. He also wanted to show some specific real examples
de trenes que ahora mismo están rodando por el mundo.
of trains that are now traveling around the world. I cannot say which is the manufacturer exactly,
Vamos arriba,
but here we have example of a European train. Above we have the train network,
protocolo
based in this case
WTB,
on the WTB protocol, which is specific for the railway world, and the railway net is based on CAN.
tenemos lo que os he
The
comentado
vehicle
antes del-
and the train buses are duplicated. We have the weak master, the strong master. In this case we have a PLC at each end of the train,
Luego, pues, en medio podéis ver que
and in the middle
los vehículos
you may see that in each vehicle there are a few less systems. And which kind of systems do we have here? Well, here we have the VCU controllers, which are the most relevant controllers. Connected with that green line, there will be an Ethernet connection cable to the graphic interface, and that is shown to the driver in the driving booth. Then we see a series of specific systems: the GCU, the door control unit, which is a specific system for the whole door programming, and there's another one for the AC, the brake control unit for the brakes, another one for batteries, and so on. And then we have the RIOM, which are those nodes where the circuitry gets connected directly to the train electronics, whether it's doors, lights, brakes, or whatever. Another example here is a European machine. In this case, there's just a single BCU, and we have both booths of the machine. Eventually, this can be driven from one side or the other. Both booths have a graphic interface connected on the Ethernet, connected to the BCU, and from the BCU we find connections to CAN interfaces, both for the vehicle bus, where we need to connect the different input and output nodes, the different realm, as well as a CAN interface with the protocol J39 that goes to the engine to control transmission. And then we have a gateway to split the network train based on WTV for the bus CAN. And here we have an American tramway that has an innovation regarding the two former examples. And here we have a Wi-Fi network connected to the Ethernet right directly to the VCUs. And it seems like a good idea, doesn't it? I feel very excited when I see it, and that is working right now in some American city. And here we can see that the CAN buses, and the vehicle bus is based on CAN. Here we don't have a train network, it's a tramway which is smaller, and in no case do additional carriages connect, and it's never going to change its structure basically. The last example I wanted to bring was this one, where everything is Ethernet based, and the increasing trend is to find this. Regarding new trains and projects, people are tending towards Ethernet more and more. So we can see the train network above, the vehicle bus below, the VCUs, the Soundmaster, Weakmaster, the driver interface, Peer's information system to show passengers whatever is necessary, and then the input and output nodes. And this will be the look of a control system's cupboard within the train. A train is something big, but we have a lot of pressure from train builders to reduce sizes. And from here, the trend is to virtualize PLCs and to reduce things as much as possible. So here we have the VCU in the middle with different extension modes, and below we have all those purple modules which are the input and output with the electronics and the cabling connected to each of them. And for many years something has been done in railway, which is safety. For more than a century. In fact, when we need to develop a control system to be implemented on the train, the rules of how to do that regarding safety are very strict, and the rules of how to test and certify that are strict too. In fact, you need to follow a V-development model that says how you should specify each system component and package, and then how you should try them out. There are different safety levels. If it's a high-speed train, that allows you to be certified in SAL 3 and 4. For normal proximity trains, with SAL 1 and 2 is enough. And what I mean here is that we really need a lot of effort here. It's something quite mature. However, we may easily find, and we made a search in the last few months in Spain, and we may easily find many examples of accidents, of train accidents. In some cases, the driver was to blame, in other cases the systems, but it depends on the case. It could also be the blame of the politicians or of the lack of investment. I'm not going to mention details. But these kind of things will not only happen in Spain. You may remember about this picture that was in Sweden in 2013. A clean lady decided it would be a good idea to walk around to take the train for a walk. She didn't know how to park it though, but it's quite surprising that it would be so easy to take a train and go for a walk. And a couple of years ago, there was a Koramis and Sophos project where they simulated a station and railway relay control, even with webcams to make it more realistic, and they put everything on the internet. And the most important thing in the experiment for me are two conclusions. First, that even the attacks made to the trainers at full speed, and it could actually derail. It's not surprising, but ethical things would not stop attacks. And in fact, one of the attackers had a good knowledge of the control system, and that is my argument when I talk to colleagues, to show that sometimes the lack of knowledge is not a limitation. Someone could learn how to do things. And if you look for examples where security has been an issue for the world of railway, there aren't that many. This has to do with the lack of connectivity of trains, traditionally, even though that is changing and is going to keep changing. But I got 3 examples. One of them was this problem in 2003 in the Washington signaling system due to the blaster virus. If you're really young, you might not know what it is. But I was working at a FNAC back then. I needed to format a few machines back then. And the message in the code for Bill Gates was quite interesting. In 2008, a 14-year-old teenager manufactured a device to play with the tramways, and probably had a lot of fun until one of the tramways derailed, and then there were 12 people injured. And when police got there, probably the fun was over. But cybersecurity there was not one of the main focal points of the manufacturer when they designed the system. In Ukraine in 2015, malware was also found in the train operator, without big consequences, however. However, there are lots of internet news, and the car hacking is quite fashionable, and train hacking too. Most news come from the UK, so we kind of let you think that they're quite good in awareness raising, until you find this. This was taken from a BBC documentary where they were showing the control system of the largest UK operator, and someone took the screenshot of the video, they zoomed, and there's a password. Just to say something in favor of the user, that was password 3. They should be at least 3 times more secure than password 1. And just to close the presentation, I just have a few slides left. I'd like to think about something. What do you think are the main risk factors, the main threat elements that we face? Because we have not targeted attacks such as Blaster or WannaCry that a couple of years affected German operator. And to clean up things from the security perspective, this shouldn't be a big problem. We have the insiders, cybercrime. We may find blackmail to an operator, even though it is not the easiest sector to obtain money from these type of attacks. But to me, the main focus and main motivation to look at cybersecurity seriously in the world of trains is terrorism. It is clear that the railway environment is an objective, is a target of terrorism. You have lots of people in a small environment, in a small space, so that is a target. And soon, for a terrorist, it will be easier, cheaper, and safer to do a cyber attack than to put a bomb on a train. And if we keep the strength to interconnect trains, we need to change the way in which things have been done. Then we have nation states. But if we don't have a username and password on the network protocols, we can't even dream of protecting ourselves from those attacks. But if we want to invade another country, terrestrial communications will be a clear objective because they are a potential threat. Let's see whether the clicker works. Regarding attack vectors and where a train network could be attacked from, if we have any sort of interconnectivity, Wi-Fi, mobile and so on, these will be one of the attack vectors. Compromising the devices that the engineers will use to update or maintain the train systems, this could be one of the attack vectors. And physically, in the train, if we manage to connect to the network, we're already seeing how the network protocols work, and of course it will be an easy way of doing this. But regarding physical security, there are minimal controls to avoid connecting from to a train swift eventually. And another of the potential attack vectors is from the comfort bus, the multimedia network, especially if you're providing users the possibility to have an IP to connect to Wi-Fi or something similar. And which challenges do we find? If you want to look at cybersecurity in the world of the railway, one of the things here is the life cycle of these systems. That could be 20, 30 or even 40 years. If I send this to a train, even though they might be able to update the software, this will be there for at least 20 years. So regarding processing, and if we want to have a TPM or any hardware security control, we'll need to resist for 20 years, and this is still a challenge. The processing capability is what it is, and it will keep being so in 30 years. So if you want future software implementation, this will be a limitation. And we have said that safety is very mature, that you really need to go through some controls and get third-party certification. And this process can be lengthy, take months, and be very expensive for the component developer. And the problem here is that if I identify a vulnerability in the component and I want to get a patch, once I have the patch ready, this cannot be implemented in the train. If a system is safety certified, first of all, it needs to go through that standardization process that may take 2 or 3 months, because you cannot change a simple code line without rectifying it. And here we're looking at the possible solutions that we may have regarding the sector to make these more agile. And if you really need to install a patch on a system, you may do so in an agile and effective way. And then we're actually sure that even though now everything is connected with cabling, the trend will be to have wireless components, because cabling in trains is costly regarding implementation and also maintenance. And we're not there yet, but in a few years we'll probably get to have a strong pressure by train manufacturers for components to be interconnected wirelessly, with the consequent cybersecurity challenge. But by then, protocols should allow us to securitize the network much better. And just to finish on a positive note, because of being quite realistic or even pessimistic for a part of the presentation, I'd like to say that even though it takes time, we can see that things are changing regarding the regulation, and train operators are being requested to really take seriously the cybersecurity aspects, and amongst them to require to the supply chain to do the same thing. So train operators, whenever they buy new trains, should have in their conditions certain reasonable requirements regarding cybersecurity, which means that train builders begin demanding from us as component builders that our systems have certain capabilities regarding cybersecurity. We also see that conferences are being held and that the sector is beginning to talk about cybersecurity. That didn't happen a few years ago, and people are actually investing. All the train builders do have departments that in some cases are very big, with hundreds of people for a big train builder, and these people work on cybersecurity. And this is a positive message that gives us certain hope for the future. And this is it, really. I don't know whether it was interesting. I do hope so. And if you have any questions or comments, please go ahead. Otherwise, just come and look at the device. There isn't that much to see, but if you're curious about it, you're welcome to come and see it. Thank you very much.
¿Alguna pregunta? ¿O queréis ver el cacharrito?
Other questions, or do you want to come and take a look?
No muerde. Pesa y otras ya.
It's very heavy, and I've been carrying it around all day. We're doing quite well for time. There's a break afterwards if you want to approach the speaker and ask the questions face to face. Thanks very much.